Here's some review of that week 12 acid-base self-assessment from class. The first question is on what type of solution it is for a bunch of different species dissolved in aqueous solutions. Just some overall guidance there, because again, people can typically find this to be one of the most challenging things. Even when you calculate the pH, once you know what type of solution it is, you just sort of apply the correct equilibrium, but determining what type of solution it is can be the most challenging. So in this case, the first thing to remember is that you should always memorize your strong acids and bases. So again, looking at sort of our key review content here, the very first thing we learned on acid-base chemistry was just the definition. A proton is transferred from acid to base. An acid is a proton donor, a base is a proton acceptor. These strong acids are shown here. There are just 6 of them that you have to memorize. The 3 acids in the HCl, HBr, HI, those are in the halogen group, and then the 3 oxyacids, HNO3, HClO4, H2SO4. Similarly, for strong bases, it's not quite as simple, but group 1 and group 2 metal hydroxides having the OH ion, and oxides having the O2- anion, is our definition of strong bases. So just memorize those, and that will get you started on this. That's also shown in this table here that also relates all of the weak acids, weak bases, and the conjugates. So just from the definition here, right, so we start by memorizing our strong acids and bases. From just memorizing that, HNO3 we can immediately identify as a strong acid. If we go down the list, NaF is not one of those strong acids or bases. CH3COH, similarly, not a strong acid or strong base necessarily. Okay, none of these work, but Li2O, Li is in group 1. If we look at it where it is on the periodic table, right below hydrogen. So this is group 1, and O is the oxide anion. So that is a strong base because it's a group 1 oxide. So just from memorizing that, we can understand that. HCl, NaCl, you see HCl there. HCl is one of our strong acids. NaCl is a salt, so maybe we need to think a little bit more to understand that. But again, if you see HCl, that's a strong acid. You can immediately write that down. Okay, now some of these next ones for neutral weak acids and bases, we can remember what the typical types of neutral weak acids and bases are, and if we're unsure, we can always check the data table. Neutral weak acids and bases, right, these are going to typically be sort of covalent compounds. These are not ionic or salts. Ionic and salts just being 2 words for the same thing, right? Anion and cation together. If I look at this, right, anytime I see a metal, I know I have a salt because a metal in this compound has to be a cation. So this Na is, again, in group 1, this is a Na plus cation. So this, again, we can first categorize this as ionic or a salt. For salts, when we think about those, we're going to need to go through this process where we break into ions and consider those as are typically the most difficult, so we'll deal with that last. But NaF is a salt. CH3COH, though there's no metals there, so this is some neutral compound, which is either an acid or a base. In this case, this COOH group, if we look at what that looks like Lewis structure-wise, that's this group. And this is a carboxylic acid. This is acetic acid, which you've used in lab. It's you need to memorize the acetate ion. So acetic acid is, again, basically something that ends up being memorized. But if you're unsure, you can just look this up in your data table, CH3COOH. That's, again, acetic acid. It's written in a slightly different format here, CH3COOH. We just put this H in front, and then the C is written here as just sort of the C2H3O2, but that's the same acid there. So acetic acid is a weak acid. It's in our table, right? These are all weak acids. Remember, this is a very common type of weak acid here. Most common when we have a weak acid, that's going to be one of these type of weak acids. We also have a few just other miscellaneous weak acids, but this is a very common type. For weak bases, they're typically in our data tables always going to be amines. So they're going to have a R is just some group, some chain of carbons or something like that, or just a single hydrogen attached to a nitrogen with a lone pair. So neutrally charged with a nitrogen in it, very likely to be a weak base. That's something you can just sort of remember. And again, if you're not unsure, just look at your data table. So CH3COOH is acetic acid, and that's a weak acid because it's in our table of weak acids. CH3CH2NH3Cl. If we look at this, this thing here with the NH3Cl, this is another salt. The Cl at the end is going to be the Cl minus anion, and that makes the rest of this CH3CH2NH3 plus the positively charged cation. So again, this is another ionic compound. We're going to need to think about the acid-base properties of each of these ions. CH3NH2, that is just a neutral compound that has, again, if we think about the skeleton structure, a nitrogen with a lone pair on it. That's, again, a typical sort of weak base, and we can look it up in our data table. CH3NH32, these are weak bases. So, again, it's right in our data table. That is a weak base. Okay, it looks like everything else here is an ionic compound or a mixture of multiple compounds. So now we need to think about salts. For salts, we have this procedure that we can use to understand what's going on with them. So here's our description of salts here. Salts and buffers, which are these other types of solutions. The first thing we always need to do is dissociate into ions. So as soon as you see something ionic, you need to break it up into its ions. That's where that knowledge of prior chemistry comes in, knowing what the ions are and what their charges are, right? You also have your polyatomic ions from this class that you need to memorize. That's on the D12 page. This all comes into play here. Then we look at the acid-base properties of each ion, and we always can refer to the neutral conjugate acid-base as needed, remembering that the conjugate of a strong acid is an ineffective base, but weak acids and weak bases are conjugate partners to each other. So again, weak acids and weak bases, as shown in our table here, are conjugate to each other, so these are conjugate partners. So a carboxylic acid has an anion, a carboxylate anion, which has a negative charge on it. Similarly, an amine, if we make the conjugate acid, that will be a positively charged cation, that will be a weak acid. Any of the conjugates over here of strong bases or the conjugates of strong acids are ineffective, and so those don't affect the pH at all. So again, since we've memorized our strong acids and strong bases, that also has us memorized our ineffective acids and ineffective bases. We get that for free. So let's see what this looks like for our last few. So NaF here, that's our next one. Again, you have to be able to break that up into Na plus and F minus ions. Na always has that +1 charge in the ion. Now Na plus is the conjugate acid of a strong base, which makes it an ineffective acid, so we can ignore Na plus when it goes into solution. That's what we are showing in this data table up here. These are ineffective and don't affect pH. F minus, on the other hand, F minus, we need to think about its conjugate acid. Its conjugate acid is HF. So we want to know, what is HF? Well, it's not one of our 6 strong acids. Remember, our 6 strong acids start at HCl, HBr, HI, and then we have the HXO. I'm just going to write it like this, like the oxy acids. So HF is going to be a weak acid. We can double check that by looking in the table. And we can see right in our data table, hydrofluoric acid, HF, is there. Again, these are weak acids. So since HF is a weak acid, that makes F minus a weak base. And so this solution here is just going to be a weak base because we have an ineffective acid which doesn't affect pH, and F minus is a weak base. Again, remember this key relationship here. A conjugate acid, strong acid, ineffective base conjugate pair, weak acid, weak base conjugate pair, and ineffective acid, strong base conjugate pair. Okay, let's look at the next ionic compound we had there. So CH3, CH2, NH3Cl. I'll just put that down here. We already broke that into these two ions. So this is a nitrogen with a plus charge. That's the cation here. Again, that is a very typical type of weak acid. To double check, we can think about the conjugate base, which is going to be neutral, because the conjugate base will have one less proton and one lower charge. So the conjugate base here is CH3CH2 NH2. And we can look for that in our data table. What type of base is that? Let's look it up. Here's our data table. Written in a slightly different form, CH3CH2 NH2. These two are abbreviated to C2H5, just adding up the two carbons and the 5 hydrogens. So this is ethylamine, which is again a weak base. Since that's a weak base, that makes this a weak acid. And again, we sort of knew that already from just the typical types of weak acids. So anything with a nitrogen with a positive charge on it is always going to be a weak acid. After a while, you can maybe just remember that, but you can always go through the process, look at the conjugate base, and double check. Again, you get all that sort of key information in the data table. The only thing you need to know is strong acids, strong bases, and then these key relationships between conjugate acids and bases. Okay, so this is a weak acid, Cl-. If we think about its conjugate acid is HCl, which is a strong acid. A strong acid has a conjugate base of an ineffective base. So Cl- is ineffective. It doesn't affect the pH at all. So this is just a weak acid in solution here. Okay, maybe I'll use the next page here to do these last couple. So HCl we said was a strong acid. NaCl is the Na plus and Cl- ions. This is an ineffective acid is Na plus. Cl- is an ineffective base because, as we saw before, conjugate base of a strong acid is an ineffective base. So this is a neutral salt, and this overall solution will just be a strong acid in solution. Okay, HFKF. HF we have looked at before already. It's a weak acid. We can look that up in our data table and find its Ka to know that it's a weak acid. Kf is a salt, so that's ionic. It's the K plus cation and the F minus anion. F minus is the conjugate base of HF. We can see that, right? Take a hydrogen off and reduce the charge by 1. When we have a weak acid and a weak base conjugate partner in solution, that's a special type of solution called a buffer. That is another thing to sort of maybe memorize is that definition of a buffer here. We'll pull that back up here. So a buffer is a weak acid, weak base conjugate pair together in solution. And so that's very, very useful. Remember, if we have a buffer, we can use the Henderson-Hasselbalch equation to calculate the pH. So again, this is a weak acid, weak base conjugate partner in solution, which is a buffer. This is not a buffer because it's a strong acid, right? So it needs to be a weak acid, weak base conjugate partners in solution. KBr, another salt. This is K plus and Br minus. Br minus is the conjugate base of HBr. It's an ineffective base. K plus is group 1, so it's an ineffective acid, which makes this a neutral salt. CH3NH3Cl. You should be able to see that NH3Cl thing there to see that this is going to be CH3NH3 plus Cl minus, an ionic compound. CH3NH2 is neutral, right? It's a nitrogen with a lone pair on it. If we look at its skeleton formula, this nitrogen with a lone pair is a weak base. We did that up above here when we decided that was a weak base. If we look here, Cl- is an ineffective base, but CH3NH3+ is the conjugate acid of CH3NH2. That's a weak acid. And this is another case where we have a conjugate acid and its partner conjugate base that are a weak acid base conjugate pair present in solution. So this is another buffer. I'll add those back here to finish out the key. Strong acid, buffer, neutral, buffer. So yeah, the key conceptual stuff here is really important to make sure you have all those key relationships down. A little bit of memorization and then a lot of just sort of looking up the appropriate data and remembering how ionic compounds work, how they go into solution as ions, sort of having that process down. These ammonium cations are a little bit new, but again, anytime you see NH3X with where X is like Cl, Br, I, etc., you can remember that this is going to be that sort of ammonium type cation plus this X anion in solution. Okay, 2 and 3 now are examples here where we're looking at Kas and stronger acids and bases and how that affects things. So in this case, we have 2 acids that are weak acids because they both have Kas that are, again, less than 1, HOCl and HC3H5O3. And we want to know which one has the stronger conjugate base, OCl- and C3H5O3- being the conjugate bases of those. So in this case, we need to remember that relationship between acid and base strength. The stronger the acid, the weaker the conjugate base. That's something to sort of memorize. It's also on our weak acid, weak base sheet here. For a weak acid to find pH, we use the Ka equilibrium. For a weak base, we use the Kb equilibrium. And again, we have in math here the relationship here that Kw is Ka times Kb. Ka, Kb are inversely related since they multiply together to a constant, so the bigger Ka is, the smaller Kb is going to be. And again, the stronger the acid, the weaker the conjugate base, and vice versa. So in this case, just from applying that, you could calculate the Kb's, but you don't have to. In this case, we can see that this is a stronger acid because larger Ka. And again, the stronger the acid, the weaker the conjugate base. So that means that this is the weaker base, which makes OCl- the stronger base. Okay, now we have these solutions and we want to know the lowest pH. This is a solution of HOCl, so this is a weak acid. This is another weak acid in solution. Again, we have their Kas given in problem 2. Number 3 is a weak acid. And if we look at this KCH3, oh, that got a little bit screwed up here, but it should be KC3H5O3. This is a weak base conjugate partner in solution. And so this is a buffer. If we look at the pHs here, this buffer is always going to, typically have a higher pH than just the weak acid by itself. So this pH, B has a pH less than C because this is just the same as B but buffered. So B has a lower pH than C. If I'm comparing A and B, they're both weak acids. But the lower pH is going to be associated with the strongest weak acid. So that's sort of the logic here. The stronger weak acid will make more H3O+ and have a lower pH. That all comes back to just understanding the basic equilibrium applied to this weak acid, weak base equilibrium. So for a weak acid, it's this equation. Ka is the equilibrium constant there. Larger Ka, that's going to mean this equilibrium, it goes further to the right. More products at equilibrium. Again, thinking about our number line here with reactants on the left, products on the right. The bigger Ka, the more products that we get. and therefore the more H3O plus we get. Larger K, more products, more H3O plus. So in this case, the stronger weak acid is HC3H5OH, so that's going to be the one with the lowest pH because it's the stronger weak acid. Okay, for 4 and 5, HNO3 is a weak, it's not weak, that's one of our 6 strong acids, so we can just use stoichiometry to get the pH. 2.5 molar HNO3 means that when we put that into solution, we'll get 2.5 molar is equal to H3O plus. And so we can just use negative log H3O plus is equal to pH is equal to, when you do that, you get negative 0.40. There's nothing wrong with that. Perfectly acceptable to have a negative pH. It just means that you have a concentration of H3O plus greater than 1 molar. In the case of 5 here, for 0.020 molar BaOH2, this is one of our strong bases because, again, it's, in this case, a group 2 cation plus this is a group 2 hydroxide. That is, again, in our definition of a strong base. So we can use stoichiometry, but in this case, we do just need to be aware there are OH is hydroxide, but there's 2 of those ions there, so that when we put this into solution, 0.02 molar BaOH2 will give us an OH minus of 2 times 0.02 equals 0.040 molar, because when this goes into solution, it makes a Ba2 plus 2 OH minus ions. And so now I can do my usual approach here. I like to do these by getting POH first, so POH is negative log OH minus, and then pH is equal to 14 minus POH from our equation sheet. When I do that, I get 1.4 here and 12.60 for my overall pH. So again, remember that for strong acids, it's typically just a single acidic proton here that goes into solution. So you just have, 2.5 molar HNO3 goes to 2.5 molar H3O plus. But for strong bases, there's a lot of strong bases where we make 2 OH minus ions, or maybe I guess even 3 OH minus ions for each amount of it that we put into solution. So remember to take into account the number of OH minus ions you get for each of your strong bases, taking into account that key factor of 2 here.